So basically we're gonna, today is all about making a full adder. Um, so that's what I've got displayed on here. This is, never mind that other screen there. Um, Last time we had the half adder that we made. So I have that here just to remind everyone what's going on. Let me plug this in just to get everyone caught up to where we're at. Just explain this a little bit. So let's see if we can stick this thing here or something like that. So this half adder basically works by um, this is one of the digits or one of the bits. So it's either going to have a 0 or a 1, and this one is also going to have either a 0 or a 1, and those are the two inputs coming in. So the result of that is this bit. So it's basically adding one bit to one bit, and the result is going to be either a 0 or 1. So for example, right now, with nothing going on, it's 0, but as soon as we put in a 1 in either location, it ends up being 1. So that's what we covered last time. If we do two of these, the result is 0 on that bit, but we have a carry bit, so it ends up being 1 that's carried through on the other side, and that's what's indicated by the up here by the light lighting up. So as far as that goes for stupid thing. As far as that goes for the, let's go back to the computer here. Oh, I need to do HDMI. Hopefully that switches over all right. There we go. As far as that goes for the logic circuit of it, the logic diagram, it looks like this. And it's a fairly simple circuit that's just using two different gates. Now for the full adder, which is lab 4, that's a little bit more difficult. The full adder has 3 inputs. The first 2 are the A and B, and the third is a carry input, which is made to be coming from another adder. So this is made such that adders can chain together, and we'll talk about that in a little bit. There's a diagram of that down there as well. And then what happens, so basically the simple way to think about it is basically you're adding 3 different inputs. You're adding the A and the B and the C in, and then obviously in that case it's going to be all zeros. Anytime where you have a singular 1 in one of these, the sum is going to be 1. That's the S. If you have 2, the sum is going to be 0, but our carry is going to be 1. So that's like the case here on this line, or rather this line, and then on this line as well. And then we go back to an input of 1 in the A, 0 in the B, 0 in the C in, and that ends up being a sum of 1. But basically, here's the power of this, because this can be combined here with a carry from another adder. So what happens is if A is 1 and B is 1 and the carry is also 1, then the sum is 1 and the C out is also 1. So they're both 1s in that case. So I'll get back up to that top bit first, but this is how it usually works when you chain all these together to make n number of bits for your adders. Basically, this one has 0, 1, 2, and 3, so this is a 4-bit adder circuit. each one of these things is represented by this. So we would need a total of, we're using 5 gates there, so we would need 20 gates to represent this. So we're not going to do that, basically. We're not going to, I mean, we would need like a really long we would need a bunch of breadboards, and it would be crazy. So instead, what we're going to do is we're just going to do one of these full adders. But it should be evident that what happens here is in the full adder, the C out goes into the C in of the next bit. So, because let's say for example, we were to have a 1 and a 1, right? Well, that's a carry, so that 1 has to go to the next bit. So that's what this is here. If it's a 1 and 1 and 1, then the sum is 1 and the carry goes to 1. So it's basically a partial sum in the S, and then the rest is going to the next adder. So as this talks about this diagram here, we implement the full adder with basically 2 half adder circuits. And the second half of that logic is used for the CN, and that's produced by the first half of the adder to get the final S output. So it looks like this, and compare the, you know, if we could compare the differences here. This top one, we have an AND gate and an XOR gate. Now we're going to add, we've basically added another XOR gate and another AND gate, and then we've added an OR gate because that's going to represent the carry out. So if you think about it, the carry out is going to result from either the result of that half adder having a carry bit, or the result of the original value having a 1 in it. So that's why there's an extra OR gate here. So basically the C out is an OR function of the half adder's carry outputs. So the reason that they use this sort of simpler diagram here is because otherwise this would become really complicated really quickly. If we did this 4 times, you can imagine how complicated that diagram would get. So and that's what's going on there. So basically, from here, what we need to do, and this is the part where now that we're in our 3rd breadboard lab, a little bit less hand-holding in terms of what to do, but basically I'm just asking you to take this and put it on the breadboard. So what you'll have to do is you'll have to figure out what all the various gates are. And the last time we talked about the gates, I had listed out for you that you would need an additional OR gate, which we didn't use last time, but it's 74. Actually, I'm going to jot it down on here so those online can get it. I want to use a different program than that. So it's OR gate that I was using was, and this is from our kit, 74 HC 7, or HCT rather, HCT N -32N. And I'm pretty sure you have that. I know that for one of these labs I have to give out some chips. It's the 139E that I'm going to have to give out, which I think we don't need yet until the next lab, so probably going to hold on to these guys until that lab. Yeah, the 139E. So So basically what's going to happen is your, uh, we've used the 74, this was the OR. We've used the 74 HCT 11E, that was the AND. We've used the 74 HCT 86E, which is our XOR gate. Pulling up the schematics for these guys. That's the Q169, that's the wrong one. 86E. So this is a quad 2-input exclusive OR gate that we used last time. And here's the data sheet for that. So you can see that we've got the ability to do multiple circuits on this one gate. In other words, if you look up here, we're going to have to use XOR twice. And then if you go back and compare that to the data sheet, that's possible to do because there's 2A, 2B, and 2Y down here. Actually, in this case, we could even use this 4 times. And then the other one that we're using right now is the AND. So I'm going to bring up the data sheet for that so you can see what you're doing here. So this AND gate also has multiple ones. The 1B, 1A, 1B, and then 1C is on the other side. And then you've got 2A, 2B, and 2C right below it. So just keep that in mind that the C is below that there. And that you can use for these 2 AND gates. And then your OR gate that we're introducing, the 32N, will be over here. So basically you're putting on one more chip on the board, and that's the OR gate. The other question that's going to come up is, well, what do you do about the extra input for the carry in? So for that, you can put another button on if you want, or you can simply just put it directly to 5 volt or negative. In other words, when you're testing it, if you don't use a button, you'll just have to move it between the 1 and the 0 manually. And that shouldn't be too bad. So I'm going to transfer over this recording. Well, not transfer over this recording, but I'm going to